Hey there everyone, this is Mr. Lopez again, and this is the Primetime Unit Test support video. This video is to be used for any mistakes that you made on the unit test. If you were marked a question that was wrong, then you can go ahead and skip through this video to see how to do it correctly and maybe see the mistake that you might have made that led you to the wrong answer. So getting started with number 1, we're asked to find the prime factorization of each number, and it also says to write the prime factorization using exponents. This is going to be very important here in how we express our prime factorization, and it wants to show our work. So for 72, remember you can use any pair you want. I want to use 24 and 3. Okay, I know 3 is prime, so I circle it. 24 can be divided into 12 and 2. I can circle 2, and then 12 can be divided into 2 and 3. Oh, no, just kidding. 2 and 6, circle the 2. And lastly, 6 can be divided into 2 and 3. So what I see here is that I have a total of 3 2's. So I'm going to write this expression as 2 times 2 times 2 times, I also see that there are 2 3's, 3 times 3. Altogether I see that I have 3 2's, so this will be 2 cubed times, I see 2 3's, so this is 3 squared. And this is my final answer. For B, this is a little bit of a trickier number. It's a little bit bigger, but I'm going to use my divisibility rules to know that 132, because it ends in a 2, it should be divisible by 2. And if I try to do 132 divided by 2, I do get 66. So I'm going to split this pair into 66 and 2. And I know 2 is prime, so I'll go ahead and circle that. This I can now see is divisible by 2 as well. I can do 2 and 33. And now 33 I know is divisible by 3, and I can divide this into 3 and 11. 11 is also prime, so I'll go ahead and circle that. My factor string, I see that there are 2 2's, 1 3, and 1 11. When I combine this, I have 2 squared times 3 times 11. Number 2 says, what number has the prime factorization 2 squared times 3 squared times 5? And we have to show how we found the number. To do this problem, I'm going to expand our expression here. I'm going to write this out as 2 times 2 times 3 times 3 times 5. And I'm going to multiply 2 times 2 first to get 4. I'm going to multiply 3 times 3 to get 9. I'm going to bring down that 5 to get 4 times 9 times 5. Now I could have just gone straight from looking at 2 squared and know that it's 4 and write that, times 3 squared, which I know is 9, and wrote that there, and brought down that 5. So either route would get you to 4 times 9 times 5. Now here I'll go ahead and I'll multiply from left to right. 4 times 9 is 36. Carry down that 5. And my last step is to multiply 36 times 5, which gives me 180. Number 3 asks to write 2 to the 5th power in expanded form and then solve. I know that 2 is my base, and 5 is the amount of times that I'm going to multiply 2 times itself. So I know this will be 2 5 times. 2 times 2 times 2 times 2 times 2. I'll double check to make sure that I only wrote this 5 times, and I see it's 1 2 3 4 5, so I know I'm good. When I multiply this through, 2 times 2 is 4, and I can write the rest of this down. 4 times 2 is 8. Carry the rest of this down. 8 times 2 is 16. And last but not least, 16 times 2 is 32. Number 4 says to write 2 different number strings that will get you 48. You also have to make sure that you don't use one as a factor. To start, I would personally make a factor tree for the number 48. And I'm just going to divide this through and see what my prime factorization is. Because if I do the prime factorization, then I know that is one expression that will definitely equal 48. So if I keep going through my factor tree here, I'm just dividing by 2 every time because I see that every number has been divisible by 2. And after completing my factor tree, I see that one expression I could do is just 2 times 2 times 2 times 2 times 3. So this would be the longest way to write this. And I know that to make a new expression, I could simply combine my my 2's and write that as an exponent and just say 2 to the 4th power times 3 equals 48. And if I check this through on my calculator, both expressions should equal 28. Something else you could do is just combine like 2 of the numbers right here so that your answer would be 2 times 2 times 2 times the product of those 2 numbers, like 6. So that's another option. And if you wanted to combine even 2 of these afterwards, you can do 2 times 2 times 12. So any way like that, as long as you are multiplying one pair of numbers at a time, your expression should still equal 48 for all answers. So these are all different expressions. And like I said, if you checked in your calculator, you should see that when you plug everything in, it should equal 48. Number 5 says to decide whether the statement is true or false, 45 is a composite number, and it wants us to explain our reasoning. So thinking of a composite number, we know that prime is a number that only has the factors 1 and itself. So composite is a number that has 2 or more factors. So thinking about this, I have to figure out if 45 has more than 2 factors. So if I were to list the factors of 45, I know that 1 times 45 is a factor pair. I know that 3 times 15 is a factor pair. I also know that 5 times 9 is a factor pair. And this alone, even if there are more factor pairs, tells us that there are 2 or more, which means it is definitely composite. So I would say 45 is composite because it is a number that has 2 or more factors. Okay. Number 6 says to give an example of a square number and explain how you know it's a square number. Now I know a square number not only makes a perfect square if you were using tiles, like this here would be represented with 3 and a 3. So this tile would be the representation of the number 9. And we know that the number 9 works. We know that we can do 2 times 2 to get 4. So 4 is an example. 3 times 3 we just did, that equals 9. You can do 4 times 4 to get 16. 5 times 5 to get 25. Any of these numbers that we just did all count as examples of square numbers. So in my answer, I'm going to say the example is, we'll just use the number 9. One explanation I can give is the same number or numbers 3 times 3 are multiplied to give you 9. Another example could just say 9 could be arranged into a square. And a third answer could just be 9 has an odd number of factor pairs. All of these explanations count as a correct answer for explaining why the number 9 or the number 16 or 25 is squared. Number 7 says to list all the factors of 50. So to do this, I'm going to think of my factor pairs first, and I know I can do 1 times 50. I see that 50 is divisible by 2, and 2 times 25 equals 50. And my last one, I know that it is also divisible by 5 and 10, and 5 times 10 gives me 50. So now I just go ahead and I put this into a list and start with 1. And going from 1, it goes 1, 2, 5, 10, 25, and 50. Number 8 says, what is the greatest common factor of 30 and 42? And it wants us to show our work. There are 2 ways to do this here. One way is to take the number 30 and find all the factor pairs, and to take the number 42 and find the factor pairs for that as well. Now that I've found all the factor pairs for the number 30 and 42, I can just look down my list and look for the biggest common factor, or the greatest common factor, which in this case does happen to be the number 6. So I would write my GCF equals 6. Another way to do this, so this is option 1. Option 2 is to use prime factorization to find GCF. So to start with that, I would make my factor trees for both numbers. So I would take the number 30 and 42 and make the factor trees. Starting with the number 30, I'll split this into 3 and 10. I know 3 is prime, I'll circle that. 10 is divisible by 5 and 2. Those are both prime, so I'm done with that. I'll do the tree for 42. I see that 7 times 6 gives me 42. 7 is prime. 2 times 3 gives me 6. Those are both prime. So now I'm done with my factor trees. The next step here is to list the prime factorization of 30 and 42. So I'll go ahead and list them out. And I see that for 30, it's 2 times 3 times 5. For the number 42, it's 2 times 3 times 7. And the next step here is to circle the common factors, the common prime factors, which I see are 2 and 3. After finding those, I know that I have to multiply the common ones together. So multiplying 2 times 3 gives me 6. And this is the GCF. GCF equals 6. In number 9, it's asking for the least common multiple of 15 and 60. There are, once again for this one, 2 ways as well. We can just list the multiples out, starting with the number 15. So we'll go ahead and do that. We'll say the multiples of 15 are 15 times 1 is 15, 15 times 2 is 30, times 3 is 45, times 4 is 60, times 5 is 75. And I'll stop there. I think 5 numbers is a pretty good stopping point, and then if we see that there still isn't any in common, then we can continue and add more. So we'll go on to the number 60. We'll start at 60 times 1, 60 times 2, 60 times 3. Oops, not 160, it's 180. 60 times 4. And that alone right there shows us that the smallest or the least common multiple is the number 60. So I'll go ahead and circle both of those and say that the LCM equals 60. Now that was method 1. If you want to go with method 2 and use prime factorization, it would be very similar to the last problem that we just did, where you would start with the factor tree and make a tree for 15, make a tree for 60. I'll go ahead and do that fast. 3 times 5 gives me 15, and both of those are prime, so that's a pretty small factor tree, but that is the prime factorization. And the number 60, I can do 6 and 10. I can break 6 apart into 2 and 3. Circle those because they're prime, split 10 into 5 and 2, and circle those because they're prime as well. In the next step, I'll go ahead and list the prime factors for 15, which are 3 times 5. I would do the same for the number 60. This would be 2 times 2 times 3 times 5. And now my next step is to see the common prime factors to find the GCF, because we're going to need the GCF in order to find the LCM in a second. So I see that 3 is in common and 5 is in common as well. So in looking for the GCF, I know that the GCF is going to be these two numbers multiplied, 3 times 5, which means the GCF is 15. Now that I have my GCF, I know that my formula for LCM is LCM equals GCF times the leftovers. I know that the GCF is 15, and I can see that the leftovers are 2 and 2. So now when I multiply these together, I can see that my LCM equals 60 as well, because 15 times 2 gives me 30, and 30 times 2 does give me 60. Number 10 says you're given the problem 3 times 3 times 5 times 5. Without actually solving the problem, how can you tell whether the answer will be odd or even? This is simply one of the rules that we talked about in class, which was that 2 or more odd numbers multiplied together will result in an odd product. And it wouldn't be a bad idea to test it out and just to be sure, write this out, see that 3 times 3 is 9, 5 times 5 is 25, and when you solve this all the way through, you would see that 9 times 25 is 225. So now I see that this did give me an odd product, and I know that my statement here is true. Number 11 tells us to use the order of operations to solve 30 minus 3 cubed divided by 3 plus 8 times 2. So I know some of you use PEMDAS and some use GEMS, so I'll just write this up here and refer to both as we go through this. So whether you're using PEMDAS or GEMS, we know that the first thing is to check to see if there's anything in parentheses or in groups. So I do see the parentheses there, but there's nothing to solve on the inside. So I can go ahead and move to the next letter, which is E on both. So we have exponents that we have to solve for. I see that there is a 3 squared, so I'll go ahead and solve for that. I know 3 squared is 3 times 3, which gives me 9. I do rewrite the rest of this in the same way, so 30 minus 9 divided by 3 plus 8 times 2. Okay, now the next step is to still check to see if there's any exponents. I see that there are none left, so I can move over to the next letter, which is the M for multiplication. And in PEMDAS, we know that multiplication and division are in the same step, so we do look for both and we work from left to right. Same thing with GEMS. We know that this is multiplication and division. And secondly, so these two are paired. Second would be addition and subtraction, which we know it's subtraction and addition on GEMS. So these two are in the same step as are these. Okay, so once again, we're looking for multiplication or division, and I see that going from left to right, the first thing I see here that needs to be solved is 9 divided by 3. I do know that this gives me 3, so I write that down. I rewrite the rest of this expression, or this equation, plus 8 divided by, times 2. And I can go ahead and look back to see if there's any multiplication left, any division left again. I do see that there's still some multiplication. And we know that anytime there's a number outside of parentheses, we're going to multiply that number times the number that's on the inside. So here we would do 8 times 2 to get a product of 16 and rewrite the rest of this again. Now I see that we're all done with multiplication and division. We're only left with addition and subtraction. Both PEMDAS and GEMS says that it doesn't matter which comes first. We'll just work from left to right. 30 minus 3 is 27. I carry down the rest. And at last, I can just solve for 27 plus 16, which does give me an answer of 43. Number 12 says, which of the following expressions are equivalent to 6 times 53? We're going to circle the expressions that are equivalent and use order of operations to prove our reasoning. And once again, we have to show our work for this. So the first step is to see what 6 times 53 is. So I'll write 6 times 53, and I know that this is going to be 318. So we will be looking for any problem that gives us a product or final answer of 318. We're going to start with the letter A here. We're going to think once again with the same mindset of PEMDAS and GEMS, knowing that multiplication and division are in the same step, addition and subtraction are as well. We have the same here for GEMS. It's just set up a little differently. Starting with A, I do see that there are two different operations. There's multiplication and addition. I do see that multiplication comes first, so I'll go ahead and solve from left to right. I see 6 times 50. I know that this gives me a product of 300. I can rewrite the rest of this. I also see that 6 times 3 is the next multiplication operation, and I can solve for that, which gives me 18. At last, I'm left with just simply addition, and I can add these two together to get an answer of 318. This here tells me that it is equivalent to what we were looking for, and it does say to circle the expressions that are equivalent, so I will go ahead and circle this expression. I'll move on to letter B. Once again, I see two different operations. I see multiplication and subtraction. Even though the multiplication has two different symbols, we know that the X means to multiply, and a dot is also the same. It's the same representation. It's just telling us to multiply as well. So I know that multiplication comes before subtraction in both PEMDAS and GEMS. So I'll go ahead and start with 10 times 53 because we're going left to right. This gives me a product of 530. I rewrite the rest, minus 4 times 53. I know that I should not do 530 minus 4 yet because there still is multiplication. So I'm going to go ahead and multiply 4 times 53. 4 times 53 does equal 212. When I rewrite this, 530 minus 212 is the last step, and it's subtraction. It's at the very end of PEMDAS and GEMS, and this simply gives us 318. So we know that this is also equivalent to what we were looking for. It's equivalent to 6 times 53 because both give a final answer of 318. We'll move on to C and see what the answer is here. I see two operations. I see multiplication and addition. We'll do the multiplication first. 6 times 50 does give us 300. We write the rest. And lastly, 300 plus 3 equals 303. So we know this is not equal or not equivalent to 6 times 53. Moving on to D, I see that there are two operations, but there's also parentheses, so that is our third operation. And looking at PEMDAS and GEMS, we know that we have to do anything in parentheses or any groupings first, so we'll go ahead and solve for 53 plus 3. I know that this is a little confusing because you see addition, you see multiplication, and you would think, oh, I shouldn't solve that yet, but anything inside parentheses is going to come before anything outside of it. So inside of it, we have 53 plus 3. This gives us 56. And we're left with 6 times 56. And this is our last step, so now I can just multiply it through. When I multiply these, I do get an answer of 336, which I know is not equivalent to 6 times 53. Even after I have this all down, I would still recommend that you plug this expression in, all of these expressions in, and make sure that they do equal what you found to be. So this, if I were to plug this all into my calculator, I would see that all of these equal what I found after using order of operations. This tells us that we used the operations in the correct order and that the ones we circled are the final answers. For the challenge, part A says to explain the mistake that was made when solving the problem below. I do see that there are a few operations here, so my recommendation is to solve it the way you normally would with what you were taught. Once again, this is either PEMDAS or GEMS. I'm going to write this expression or this problem, 18 minus 6 plus 2 times 3. I know that there are no parentheses. I don't see any exponents. I do see multiplication. So I will do 2 times 3 to get 6. And I'll rewrite the rest of this. I see that there's only subtraction and addition left, and we're able to work from left to right with these because they can be done in any order. 18 minus 6 gives me 12, and 12 plus the rest of this, which is 6, gives me an answer of 18. So now looking at what they did, I can see that at first they kept this 18, they kept this 6, so this must mean that they multiplied 2 times 3 first to get this. And we see that what they multiplied here gives us the same thing that we did in our second step. So we know that's not where the mistake happened. In this next step, we do see something different. We see that we have 12 plus 6. They have 18 minus 12. So this looks like we went from left to right and did 18 minus 6 first. They went from right to left and did 6 plus 6. But the tricky part here is that this minus sign in front of the 6 is actually telling us that that's a negative number. So negative 6 plus 6 cannot equal negative 12. This would be negative 6 plus 6 equals 0, which means those two would cancel out, leaving you with just 18. So our explanation could look a little something like this. So a good explanation would be they should have solved for -6 plus 6 instead of 6 plus 6 to get 0 instead of 12. Part B is a little bit trickier. We're combining two of the things that we've done. We've found area, but now we're kind of working backwards, and we're given the area, and now we have to find the side lengths. We also have talked about common factors. So in doing this and solving it, we have to find a common factor that is shared between the numbers 42, 120, and 54. The reason for this is because we know that all of their side lengths, the first box, the second box, and the third box, have to have the same side length. There is a long way to this and a short way. We're going to start off with the longer way, but I will fast forward to when I have all of this done, all the work. But if you look for all the factors of 42, of 120, and 54, we should be able to spot all the common multiples fairly easy, and whatever that common multiple is going to be the side length A. And I know we've done problems where we've had a side length of A and then the lengths on the bottom of B and C. So this is pretty similar. It's just it has an extra section, so we're going to call it D. So after we find all the factors, like I said, any common factor can be placed into A, and then we can just solve for B, for C, and for D. So I went ahead and I found all the factors of 42. I did stop at 6 for the factors of 120 and for the number 54 because I found some common ones. I see that 2 is in common between all of them. I see that 3 is in common between all of them. And I also see that the number 6 is in common between all of them. So pretty much any one of these three can be placed into A, and whatever the factor pair that goes along with it to give you either 42 or 120 or 54 is going to be side length B, side length C, and side length D. So if I look at the first common factor, I see that 2 is a common factor between all of them. And this is what I was going to say at the beginning. The shortcut to this would be to see any obvious common factors based on their divisibility rules. So because I do see that they're all even, I know that they're all divisible by 2. So if you wanted to skip the step of finding all of the factor pairs, or at least most of them, you could just look for divisibility rules, find a common one that they have, and then use that number for side length A. So if I'm using 2 for A, this means that A times B will have to give me 42. So this means 2 times something needs to give me 42, and in this case, 2 times 21 gives me 42. When I look at the next box, I know that A times C is going to have to give me 120. I know that this will be 2 times something will equal 120. In this case, it is 2 times 60 equals 120. Just like we did for the last two, I know that for side length D, I'm going to have A times D equals 54. I know A is 2, so 2 times something will give me 54. And in this case, it would be 2 times 27. Gives you a product of 54. The same thing can be done with the number 3, with the number 6, or any larger number that they have in common. And you would be able to find side lengths that would work for this area model.